Hey everybody, I'm back. In this video we're going to talk about vertical stretching and compressing. So if we have the graph of y equals f of x, which is our parent graph, and we multiply that graph by some constant multiple, so this is a coefficient, it's outside of the function, and it affects vertical things because it's outside of the function. So if a is bigger than 1, then I'm actually going to be stretching the graph. Just like as before, what you see is what you get on the outside of the function. So let's say there's a 2 out there. All my vertical movements are actually going to be multiplied by 2. If there's a 3 on the outside, all of my vertical movements are going to be multiplied by 3. But if a is smaller than 1, if the absolute value of a is between 0 and 1, then I'm going to, let's say a is 1/2. If I'm multiplying by 1/2, all of my vertical movements are going to be multiplied by 1/2, which actually makes the graph compress a little bit, which is why this is called a compression. But again, it's what you see is what you get. What the a value out in front of the graph does is it changes your vertical movements. It's a multiplier for your vertical movements. Exactly what you see is what you get. So, for instance, if we have something like f of x equals 2 times the absolute value of x, let's graph this and see how things change. Now, we haven't done an absolute value of x graph yet. So I'm going to go through and I'm going to graph the parent function first. And then we'll talk about what the 2 does to affect that. Was this called f of x? Yeah, okay. So if this is x and this is y and our scale is 1 in both directions, let's first start with g of x being my parent function, the absolute value of x. Now we graphed this on the calculator, but we haven't actually graphed it by hand yet, so let me show you what that looks like. This is actually a very easy graph to memorize. It starts at 0, 0, and the pattern is we go up 1, we go out 1. 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 And that's going to continue in both directions forever. Okay. Now again, just like I said in the previous video, you should try in your mind to separate the vertical movements from the horizontal. It's tough with this kind of graph because they're both the same, and so we just want to lump them together. But we want to think of these things independently. Our vertical movements are independent of our horizontal movements. In this case, it's just that in our most basic function, the vertical movements are 1 and the horizontal movements are also 1. So now let's graph the function that we're interested in, which is 2 times the absolute value of x. So there's no shifting happening here. I don't have anything being added or subtracted inside the absolute value or outside the absolute value. And so there's no, my starting point is still going to be 0, 0. But now, all of my vertical movements are going to be multiplied by 2. So when I am going up, normally I go up 1. But if I multiply that by 2, I'm going to be going up 2 now every time. So I go up 2, I still go out 1 because my horizontal, this is affecting vertical change. This is saying whatever we do vertical, do it times 2. Okay? So horizontally, I'm still going out 1 every time, but vertically I'm going up 2, out 1, up 2, out 1, up 2, out 1, up 2, out 1, and so on and so forth. I'll stop it there. I know that I should be extending it to the edge, but I don't want to get into my writing here. So my new graph This would be nice if I could actually hit the points. Okay. Not the best, but... And these don't have to be perfect. I want to see the points that you're plotting. These points are important. I want to see them all. But if you mess up the line that goes through them, that is okay. So 2 times the absolute value of x looks like this. And you can see, it just looks like it's stretched vertically. Like if I take the red graph and I pulled up on it, I'd get the blue graph. Okay? So that's a vertical stretch. Now let's talk about horizontal stretching or compressing. So now you can see I have this b value, which is still a constant multiple, but it's inside the function. And since it's inside, it affects horizontal movements. But instead of multiplying all of my horizontal movements by b, I'm actually going to multiply all of my horizontal movements by 1 over b. So that's what this is all about right here. And so just like normal, if you're inside the function, it affects horizontal movements, and it's the opposite of what you see is what you get. So if I had a 1/2 on the inside of a function, I would actually multiply all of my horizontal movements by 2. And if I had a 2 inside the function, I would actually multiply all my horizontal movements by 1/2. And so if I'm between 0 and 1, it's actually a stretch because I'm multiplying by the reciprocal. And if I have a 2 inside, if I have something bigger than 1, it's a horizontal compression because, again, I'm multiplying all my horizontal movements by the reciprocal. And so if there's a 2 inside, I'm multiplying all my horizontal movements by 1/2, which compresses the graph. So let's look at this. We're going to do this with a quadratic. Okay. Again, we should know what the parent function of a quadratic looks like. I'm going to keep my scale 1 in both directions. Okay, so we have f of x is the quantity 2x squared. So this 2 is inside, which means it affects horizontal movements, and it's going to be the opposite of what you see is what you get. So there's no shifting going on here, so I'm going to start at 0, 0. Now normally, I would go up 1, out 1. But instead, I'm going to go up 1 because my vertical movements have not been affected. I'm going to go up 1, but out 1/2 in both directions. Again, vertically, this has not been affected, so I'm going to go up 3 from here, 1, 2, 3, out 1/2. So my vertical movements are unaffected. I'm going up 1, 3, 5, 7, 9. Horizontally, instead of going out 1 every time, I'm going out 1/2. So up 1, 2, 3, 4, 5 from there, out 1/2. Up 1, 2, 3, 4, 5, 6, 7, out 1/2. And there is my quadratic. And you can see that it has been compressed horizontally. And I know you're thinking, well, that also looks like it's been stretched vertically. Yes, because the quantity 2x squared is also 4x squared. So that would be like multiplying all my vertical movements by 4. But notice how I got all of these points I was able to plot. Thinking about it this way, I was able to plot 1, 2, 3, 4, 5, 6, 7, 8 points, and 9 including the vertex. If I thought about it this way, I would start at 0, 0. I'd go up 4, out 1, which would give me these 2 points. If I was thinking about it this way. And then normally I would go up 1, and then I'd go up 3. So going up 3, then my next move would be 12. So go up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Out 1. That gives me these. So I'd only have 5 points if I thought about this as a vertical stretch, but I get 9 points when I think about it as a horizontal compression, which is actually beneficial. So when I'm given the problem like this, I want you to think about it like this. I don't want you to change it. I want you to be able to work with the 2 inside, okay? Because you're not always going to be able to bring that number out in front, like with a square root function. All right, I will see you in the next video where we're going to just put everything all together.